All right, let's focus on the barrier penetration problem now in detail, okay? This will look quite a bit like the finite well problem that we solved earlier. It's a little bit more complicated, and so this time, instead of going through it step by step in great detail, I'm going to go through it with you on PowerPoint. Well, you'll still see all the steps, but we'll focus more on the big picture than on understanding each particular line. Okay? Well, you'll see. It won't be so bad. One moment. Okay, very good. Yes, okay, I'm sorry. Very good. Let's get started. So here's the scenario, okay? Let's suppose we have a barrier of width L and height U0. Particles will be incident on this barrier from the left with energy E, which is less than E0, okay? And we'll set the problem up like this. For reasons that'll become clear in a few minutes, it's convenient to put the right edge of the barrier at x equals 0 and to put the left edge at x equals minus L. It doesn't really matter, but it just makes the algebra look a little bit simpler, okay? Once again, we're going to divide the problem into 3 regions. The region on the left, region 1, the barrier region, region 2, and the region on the right, region 3, okay? We suppose that in region 1, we have an incident wave, okay? And we have the possibility of a reflected wave. In region 2, we'll see we have exponentially damped waves, but then in region 3, we have the possibility of a right moving wave. By the way, there's not going to be a left moving wave in region 3, simply because we're not setting the problem up that way. In our problem, the incident wave only comes from the left, not from the right. There we are. So this is the form of the wave function in the 3 regions. In region 1, it's a general free particle wave function, a e to the I kx plus b e to the minus I kx, representing a wave moving to the right plus a wave moving to the left, the reflected wave. In region 2, where the potential energy is greater than the kinetic energy, or greater than the total energy, the wave function has this form. The solutions look like exponentials, not complex exponentials. So we have this term, c e to the minus alpha x, which represents a decaying exponential. As we move to the right, the amplitude decays. And then we have this term, d e to the alpha plus x. This would represent something that blows up as we move to the right. Now, it's a solution of Schrodinger's equation. It's not yet clear if it's an important part of this problem or not, but we have to leave it in for the moment. Finally, on the right-hand side, in region 3, we assume we have this, which looks like a free particle wave function for a particle moving to the right. Okay, so that's our setup. We have our barrier potential. In the 3 regions here, the wave function has somewhat different forms. And now what we're going to do is to use the boundary conditions at x equals 0 and x equals minus a to match up the solutions. And by assuming that the wave function is continuous at each boundary, and by assuming that its first derivative is also continuous at the boundary, we'll see that we can get an expression for f in terms of a. And that's our goal, because if we know f in terms of a, then we can figure out the probability of transmission. All right, so that's our manifesto. Now let's carry it out. Looking first at x equals 0, let's see what we have. So the boundary condition there says that the solution in region 2 for x equals 0 must equal the solution in region 3 for x equals 0. And looking at these 2 equations, you can see that when x is 0, the exponential terms are all 1. And so we have c plus d equals f. Okay, our first relationship. The second requirement is that the first derivative of the wave function be continuous at x equals 0. So taking the first derivative of this term here and setting it equal to the derivative of this one at x equals 0 gives us this second equation, minus alpha times c minus d is equal to I times k times f. Okay? Just dividing both sides by minus alpha gives us this expression here. C minus d is equal to minus I k over alpha times f. Okay? So that's our second equation. First equation, second equation. Now, the next step is we're going to add the first equation and the second equation. This will have the effect of eliminating d and giving us a relationship between f and c. Okay? First step on our path. So let's do that. When we do that, we find that 2c must be equal to 1 minus I k over alpha times f. Or just solving this for f, we get an expression for f in terms of c. Okay? So we have f in terms of c. So now if we can just find c in terms of a, we'll be all set. Great. Now, as we're doing this, there's one other thing I want to show you. This is kind of a detail, but it'll be important in a moment. Okay? Looking back at this, you can see that alpha minus alpha times c minus d is equal to ikf. But the other way we could have done this would be to combine this expression with the first one to eliminate f. Then we get minus alpha c minus d is equal to ik times c plus d. Okay? Or we could rewrite this as an expression for d in terms of c. D then would be equal to minus, and now we have quantity alpha plus ik divided by quantity alpha minus ik times c. Now, the reason this is interesting is that this term alpha plus ik over alpha minus ik, that's some complex number, but it's a complex number of magnitude 1. Okay? Meaning that this expression tells me that the magnitude of d is equal to the magnitude of c times a factor of magnitude 1. So magnitude d is equal to magnitude c. Okay? Just hold on to that for a moment. So far, by using the first boundary condition, we have an expression for f in terms of c, and then we also have a relationship between c and d. Let's go on. So this is what we've found so far. And now let's take a look at the other boundary condition, the one at x equals minus L. Once again, at x equals minus L, we must have the wave function in region 1 be equal to the wave function in region 2 at this point. And their first derivatives also have to be continuous. Okay? Looking at the first expression, we get this. Now, it looks more complicated because we can't drop out the exponential terms because we're not at x equals 0, we're at x equals L. And we get a e to the minus ikl plus b times e to the plus ikl. Remember, x was minus L. That's why the exponents seem to have changed sign. Anyway, this is going to be equal to c times e to the plus alpha L plus d times e to the minus alpha L. Okay? Now, we're going to make an approximation. So far, we haven't made any approximations, but now we're going to make one. Let's assume that alpha L is much greater than 1. From a practical point of view, it means that the wave function decays a lot from the left-hand side to the right-hand side. Okay? Now, that's not always the case. I suppose if the barrier were very, very thin, we wouldn't be able to do that. But most of the cases that we're interested in are ones where the barrier is a little bit thicker, and the wave function really does decay quite a bit as we go from the left side to the right side. In that case, you can see that this term is much, much larger than that term because C and D have roughly equal magnitudes, but this term, e to the plus alpha L is very large compared to this term, e to the minus alpha L. And that's because alpha L is a is a number much larger than 1. So in that case, we can neglect the second term. We'll drop the second term, okay? And then that makes our lives somewhat easier and produces a much more manageable result. If you want to see what the problem looks like if you don't make this assumption, you can look in our book and you'll get it. And the result is a very complicated expression, which is valid, of course, but which I think sort of obscures the interesting result. So that's why we're focusing on this case. So we're going to assume that we can drop this term. And let's see what that leads to. So now we can replace this expression here by this one. A e to the minus ikl plus b e to the plus ikl is equal to c e to the alpha L. From the continuity of the first derivative, from this expression, we get something similar. Here it is, ika e to the minus ikl minus b e to the plus ikl is equal to minus alpha c to the e to the power alpha L. And we can rewrite this just by dividing both sides by ik and get this. And then we'll do just what we did in the previous case. We're going to add the first equation, this one, to this one, the second equation here. And that will eliminate the factor that has b in it, okay? So if we combine these to eliminate b, we get 2a e to the minus ikl is equal to 1 minus alpha ik times c e to the alpha L. Okay? Or dividing both sides by this term and this term, we get an expression for c in terms of a. And of course, that was our second goal. So c then is equal to minus 2ik over quantity alpha minus ik times e to the minus ikl times e to the minus alpha L times a. It's kind of a mouthful, but it's not a simple expression, but we have an expression now for c in terms of a. So all we need to do now is to put these two expressions together to get an expression for f in terms of a. And that's what we can use to calculate the tunneling probability. So let's go ahead and do that, okay? So finally, combining these two expressions and then dividing both sides by a, we get the following. F over a is equal to minus 4ik alpha over alpha minus ik quantity squared times e to the minus ikl times e to the minus alpha L. Okay? Now, really, we'd like to find the transmission probability. And so to find the probability, we need to take the absolute value squared of both sides. And that's going to give us the expression that we want, okay? So the last step here is to take that absolute value squared on both sides. So absolute value squared of f over a, that's the transmission probability, okay? And then this turns out to be equal to, as you can easily show, 16k squared alpha squared divided by quantity alpha squared plus k squared squared times e to the minus 2 alpha L. Okay? Finally, let's just rewrite this so that for these factors in the front, instead of having k and alpha, we'll write it in terms of e and u. Okay? And when we do that, it's just a little bit of algebra. We get 16 energy times quantity u naught minus energy divided by u naught squared, okay? Times e to the minus 2 alpha L. All right? Just to sum up, the transmission probability is equal to a number, 16, times this quantity, which is typically a number on the order of 1, okay? Times e to the minus 2 alpha L, an exponential factor. If alpha L is much bigger than 1, then this is a small number. And it depends very, very strongly on L, okay? That's our result. So the tunneling probability is given by this expression, and it decays exponentially with distance. Here, let's stop here, and then we'll do some examples.